Good evening. I'm Horst Simon. I'm welcoming you to the annual Top 500 Birds of a Feather session. And as every year, we have a program of statistics, awards, and then hopefully lots of community input. What we're going to do is first awarding the number 1, 2, and 3, and the number 1 in Europe and the Green 500 list, plus a number of special awards because we have the 50th list. Then Eric Strohmeyer, who is sitting right next to me, will give highlights of the 50th list. We'll have Mike Carew from Sandia, who will talk about... Your mic's not on.
Embarrassing.
Sorry. Then we'll have Mike Carew from Sandia, who will talk about the HPCG benchmark. We have a special presentation by Prabhat, a colleague from us at Berkeley Lab, who will talk about benchmarks for machine learning. And then hopefully we have a lively question and answer session. I also want to point out that the Green 500 will have a Birds of a Feather on Wednesday at 5:15, same time. And the Graph 500 also on Wednesday at 12:15 at these rooms. There's also the Virtual I/O Institute that is launching an I/O 500 that also has a Birds of a Feather. You may notice that we don't have any more an HPCG benchmark Birds of a Feather because that has been integrated, and so it all saves us an hour and a half time. Thank you, Mike and Jack. I also want to point out that ISC, the sponsor of the Top 500, has a booth at number 813. If you pick up the questionnaire, which is right next to the registration desk, answer 4 questions, you'll get this Top 500 little robot as a special gift, and I hope you all pick one up and visit the booth at 813. And I also would like to invite you to consider coming to ISC 18, which I happen to be the general chair for in Frankfurt in June of 2018. So with this, we want to move together, Jack, Eric, and I, to an award for number 1, 2, and 3, and the other awards for the Top 500 list. So we'll start out with number 1, the Top 500, number 1 ranked system continues to be, as in the past, Sunway Taihu Light at the National Supercomputing Center in Wuxi, China. And I'd like to ask Haohan Fu to come to the stage and receive the award. Congratulations.
Congratulations.
Thank you. Congratulations.
There you go.
Do you have another? Two.
Either way.
So let's do the... Yeah. Thank you very much. Thank you.
So it is my pleasure to hand over the awards for the number 2 system. It's again the Tianhe 2 system in China at the National Supercomputer Center in Guangzhou, which has had quite a bit of history by now. If you watched the last talk we gave, it has actually the reputation or the distinction right now to be the one system in the Top 500 which has accumulated the most normalized flops over its lifetime ever. So with that, I'd like to call Yutong Lu to accept the award. Yutong, congratulations.
Thank you.
And you want one of these?
Okay.
Thank you.
And I have the honor of awarding the number 3 system. This is the Visdane system, which is located in Lugano, Switzerland, the CSCS supercomputing center there. So I'd like to invite Lorenzi Micheli and also Pascal Barbalosi to come up and receive the award. I'll get it right away. Congratulations. Congratulations. That's right, even though I massacred your name. So let's do this here. Yes. Perfect. Nobody's taking, oh, they're there. Very good. Thank you so much. Congratulations. Oh, yes. Yes, we should hand out these things. And I also have the honor of giving out the #1 system, the award for the #1 system in the U.S. The #1 system in the U.S. goes to the Titan system at Oak Ridge National Laboratory. It's the Cray system. It's actually quite an old system today, and it's showing its age by moving down in the list. It's #1 in the U.S., but #5 in the top 500. So I'd like to invite Larry Holzman and also Buddy Bland to come up and to receive the award. Yet again for the outstanding achievements. And nobody's taking pictures.
Pictures. That's fine.
We got a few people. Okay. Thank you so much. Oh, yes, I forgot.
So, you know, we like to keep things interesting in that spirit, or maybe for the lack of preparation on my side for the BoF session. We're going to give out 3 awards, and we don't know if the recipients are here, and I don't have slides for it. Okay? So the next awards are for really regions which not necessarily show up in the top 500, in the top 10, but we like to give them an award for being the top system and having a consistency in supercomputing in other regions in the area, geographical diversity. So the first system, the first award we like to give out is for Shaheen 2, a Cray SC17 XC40 system at the King Abdullah University of Science and Technology in Saudi Arabia. So I do have somebody here to accept this award. Great, thank you very much. Yeah.
Sorry. Okay, I guess somebody's taking pictures. Thank you. Congratulations.
Thank you very much.
Congratulations.
Thank you. And these are empty folders if somebody needs to get one for taking home your certificate. The second surprise certificate is for the #1 system in Australia and Oceania, which has 1.68 petaflops and has been on the top 500 for a couple of lists too. It's origin of a Fujitsu, Primagy, and Lenovo Next Scale system at the National Computational Infrastructure National Facility, NCINF, in Australia. Is there somebody here? Yes, we do, indeed. All right.
Congratulations.
Congratulations.
Any pictures? No pictures. You stand.
Anybody taking a picture?
Somebody's taking pictures. Okay.
Yeah.
Okay.
Okay, thank you.
Thank you.
Take one of these. And last but by far not least, Lengao system in South Africa is going to get a #1 in Africa award for 1.03 petaflop. So all the awards at least go for systems over a petaflop. And it has been the #1 system for Africa for a couple of editions as well, and we hope it's going to stick around for a little while. So happy Sipoli. Thank you very much.
Congratulations.
There you go. Thank you. Thank you very much. And I think we're going to come back to some mystery awards later, but for now we are done with the awards. And okay, we missed that one. We haven't done that one yet. Okay. So traditionally for the last couple of years, we have also been giving out the Green 500 awards, so who is going to do that?
All right, this year's #1 supercomputer on the Green 500 list hit a whopping 17 gigaflops per watt. To give you some perspective, that gets us over a third of the way towards getting an exaflop supercomputer in a 20 megawatt thermal envelope. So if we were to extrapolate this system out to a exaflop, we'd be about 60 megawatts. So we're rapidly on our way towards achieving the 20 megawatt system for exascale. And the #1 system is Shobu System B. This is from Advanced Center for Computing and Communications, Riken in Japan, and I believe that we have there we go, thank you. We have representatives from Riken as well as Pezzi here to accept the award.
That's great. Congratulations.
Aaron?
Congratulations.
Congratulations. That's right. It's good to see you again.
Okay. Congratulations.
If you all stand here.
Yeah, well, it's two of those.
This is it.
I'll stand at the right.
Thank you. Congratulations. Thank you.
Thank you.
Congratulations again.
Thank you.
I'm going to get. Thank you.
Take as many as you need. Okay, and now you have to stick with me for a second while I switch slides.
Are you here by yourself or did you bring family?
I have my wife and youngest kid. They're off doing something fun. I'm not sure what. How about you? Just here.
Just here by myself. I'm realizing I really should be taking my family with me.
Boss, do you want to do that or should I?
It's nice. It's nice. Doesn't happen every day.
Okay, so something we have been traditionally doing here is promote and help and give more attention to the student cluster competition, which these days feels like they don't really need that anymore. They get a lot of attention, but we like to continue it because it brings more attention to us as well. So in that spirit, here is the top list from the student cluster competition in terms of who participated, from which university, what system they were compiling, and so on and so forth. And traditionally, while there is the big awards ceremony for the student cluster competition, I believe on Thursday, what we do here is just highlight the HPL number those students have achieved. And before I switch over to announce the winning team on the HPL benchmark for the student cluster competition this year, it's just a little announcement that we also started a new effort that we are going to collect within the Top 500 website. We collect the results, the history of the results for the student cluster competitions worldwide, and we are going to compile a running list of all the results of the student cluster competition to see how this cluster competition would have fared against past competitions and so on and so forth. That should be forthcoming soon. We're in the process of setting that up. And it has been announced here. You find a poster about this if you go to the student cluster competition area. And with that, the student cluster competition highest LINPACK winner this year is going to be the Nanyang Technological University with a score of 51.8 teraflops. Congratulations. So do I have the winners in the room? Can they stand up? There they are. So big round of applause. And good luck on Thursday for the big competition. Okay? Thank you. And with that, I think we are back to the program. Thank you.
Back to you.
Which would be actually my part, so I could hand it back to Horst to introduce me, but we could just switch over. My microphone? No.
No, it's coming.
So with this traditional part for the BoF is that I give a presentation about some of the highlights of the Top 500. And this is going to be a slide set which is going to look much more familiar to you if you have seen the last presentation. That was a very different analysis we performed. So this is more the highlights as you have seen them before, just updated. So the top 10, we have 2 new systems, or at least 2 upgraded systems in the top 10. The number 4 system is a new system in Japan, Gyoku, which is actually the same architecture as the system which just received the Green 500 number 1 award. It's a Zettascaler 2.2 system. It's using a very special or new accelerator, the PETC2 accelerator at 700 megahertz. And it got the distinction not only for being the most efficient architecture line in general, but also the distinction for being the system in the list this time around with the highest level of concurrency with almost 20 million cores. It's a factor of almost 2 higher than the number 1 system. And both of those systems are, again, almost an order of magnitude more than most of or any of the other systems in the top 500. So it's really an unprecedented level of concurrency you have to program on these systems. And it's going to be interesting to see actual application in those systems. If you look carefully into the data, you could actually expect that the system would even perform a little better than they have. And I suspect that they were just running out of time in terms of the LINPACK measurements. I wouldn't be surprised if they even show better measurements in the future. The second system, which is you find on the last list as well on the lower rank, is actually a total upgrade, not just an upgrade, it's the second part of the machine which was installed. And by that, I mean the Trinity system, this part of the Trinity system is very different from the original part. This is the part which is built out of the Knights, and I'm almost mixing up Knights Landing chip. So it is the part which doesn't use any host processor, any Xeon processors. It's similar in architecture to the Core system, which is just behind it. And it is at position number 7. So 2 new systems in the top 10. Otherwise, the top hasn't changed that much. Overall, this is something we have seen the last couple of years, that the rate of change throughout the list as well as on the top has slowed down, so that is not really something new. A corollary to that is that the average system age in the list, its inventory, that the average system age has increased. Used to be a little over half a year, and now we are in a range of about average age of 1.5 years. That hasn't really changed, and probably will not change in the near future, because it really reflects the change in undergoing growth rate due to Moore's law. It doesn't pay off to change the system every 3 years, because the delta you get for the new system doesn't justify buying the new system. You're better off saving the extra money another 2 years and then buy a new system every 4 or 5 years. One statistics we looked at a couple of years, and which has shown some abnormalities over time is that question: what is the shape of the distribution? And one quantifier, a single number quantifier for the shape of the performance distribution in the top 500 is simply the position, the spot at which half of the performance of the total list has been accumulated. And there was an anomaly that basically it took less than 20 systems, a couple of lists back, 3 years back, took less than 20 systems to accumulate half of the performance of the overall top 500. And that was a clear anomaly, and it has rectified itself more or less by now. So some of these anomalies, they come and go, and it's a little harder to understand what drives their appearance and drives their disappearance. But I'm happy to say, at least for this, in this aspect, we are back to how the list used to look like for a lot of the history. This is the performance growth rates. You have seen this slide probably before, and if you look carefully into the slides, you see that the number 500 as well as the average or sum of 500 list curves are actually exponential, but they are actually nowadays composed out of 2 different exponential curves. One up till either 2008 or 2013, depending on the curve, which was the old growth rate, and now since 2008 or 2013 for the average, a new growth rate which is substantially slower than the old trends we had seen in the top 500. There is only a signal for 2 growth rates in the data. There is no signal for a 3rd growth rate, and it's a very abrupt change for both of those lines, but they don't coincide. That's the curious thing. The interesting thing is, of course, if you project it out, that we see a shortfall in performance, and if we just pull down a parallel line for the number 1 performance, we see that shortfall by 2020 is basically the difference between having an exaflop system or not having one. And that's one of the big questions in the room is, are we really going to have an exascale system by 2021? What is it going to look like and all those things? It's an open question. The corollary to having a knee in our distribution function is simply if we compute annual, let's say November to November growth rate, performance growth rate in our curves, we see an up and down, and again, for the average growth rate in 2013, there was an abrupt change. Up till 2013, the growth rate was substantially higher than Moore's law, and the average of it was very consistent. And since 2013, is noticeably slower than Moore's law, and again, it seems to be very consistent. Whichever way we look at the data, it comes out the same way, that there is a knee in the distribution curve, and it's a very abrupt knee. It's not something which happens smoothly. So in terms of statistics, you saw the headlines. China now has more systems installed than the United States. That has happened before, but it was almost more or less a dead heat. This time, for the first time, China is actually like 10% ahead of the US, so more than 50 systems delta between China with over 200 systems and the US barely 150. So that's really different from the past. It's followed by Japan as well as the traditional European countries. If we look at the distribution over the history of the top 500, how this actually has developed, you see that the US share was always by far the largest one, followed by Japan and the European countries. And China started to come into the list about 10 years ago, built up somewhat slowly up till about 2-3 years ago, 2013, 2014, and at that point it really came in very strongly, exploded, and has now a market share which is actually larger than the United States. The statistic which is a little harder to pull out of the database, and we haven't published that online yet, but we're going to do so in the future. We have to add some tables which only live on my laptop right now to the main database, is actually the statistics of where these systems are produced. So what I'm doing now is I'm going to show you where these systems actually have been manufactured. So next slide. This is the performance as it has grown, and China is #1 in performance too. And this is where the slides are actually produced. So that's the one I was leading towards to. And what you see is that what happened 2 years ago, 2.5 years ago, is actually a concerted effort from a variety, like 4 different Chinese manufacturers, to start producing their own cluster-based systems and MPP-based systems. They're building their own supercomputers, and they're selling them not only in China, but also outside of China, mostly inside of China. So that has coincided with the big jump of Chinese consumer, is also that China started producing their own systems, and certainly they are producing it for the worldwide market. It's still, the most systems are still produced in the US, but that's going to be interesting to see in the future if that stays that way or that swings around as well, or if we're going to have a situation, I wouldn't say again, but almost again as in the 1980s, where there were Japanese vector computers which were produced in Japan and used in Japan, and American vector computers which were produced in America, in the US, and used in the US. And we might head back to that, but we don't know. But it's very interesting. It's something we definitely want to watch in the next couple of years, and we're going to introduce these tables and these categories online as soon as we get around to it. Companies, HPE has been the #1 for a variety of lists. HPE has a long history in 2 aspects in the top 500. It has always had a lot of systems in the list, or most of the times a lot of systems in the list. And B, I think it is the company in the top 500 which has bought the most other companies who had systems in the top 500 at some point. So in this blue pile there is hidden a couple of SGI systems, because that's one of the last companies they bought, but they bought Compaq, they bought Convex, they bought a couple of others. Okay. So HPE, and now surprisingly actually the Japanese companies are already in the following spots, #2 and 3, if you just look at the number of systems. The Japanese companies certainly are jumping up. Part of the Lenovo systems are inherited from IBM when Lenovo bought the IBM server business from IBM, but part of those are already their own design and their own manufacture. But Inspur's definitely is Chinese built systems. There is no way around that. Cray is #4 in this category if you just look at the number of systems. And then again, you see Shugon, another Chinese company, following. So the Chinese manufacturers are certainly going to play a more dominant role, at least by system share. And if you look at the performance share, it switches around a little, but it's actually not that different. HPE is the #1. It's followed by Lenovo. And Cray, typically in performance statistics, Cray features higher because Cray sells very big systems, especially in the US, but actually worldwide. So Cray is typically higher, again followed by Shugon already. So the Chinese manufacturers by no means build small systems only. They build average size systems across the whole range of systems which are employed in industry or research centers. And they accumulate performance just as well as other companies. The only slide I'm going to show this time about the top 50, the real high-end, even if you look at system shares in the top 50, Cray is the market leader in that very narrow market segment. And that has been like that for a while, followed nowadays by HPE, and most of those 7 HPE systems are actually SGI-based, technology-based systems, which HPE continues to maintain and sell and develop further. So that's nice. IBM is still strong in the top 50, but that's the basically holdover blue gene-based systems in that list. And the Chinese manufacturers have not made a big impact there yet, but again, it's going to be interesting to see when that happens. Okay, accelerators in terms of technology categories, we have been looking at this. The number of systems which uses accelerators has been growing for a while, and we see the different generations of accelerators at the bottom for the different generations of NVIDIA GPUs, and a little further up, red and green, for the different generation of Xeon Phis. Those are the two dominant families. At the very top, you see a little light blue category, which is the PETC accelerators, which are used in this new Zettascaler 2.2 architecture, which is now at number 4. There is a total, I believe, of five-ish systems in the list already for that. So that's going up nicely. For me, the more interesting statistic in terms of accelerators is actually how much do they really accelerate the list, which is performance. So if I look at performance, at the performance share, the systems with accelerator contribute to the overall performance in the top 500. I see that that has been surprisingly for the last 4 years rather steady, rather constant. So about a third of the list in terms of performance is driven by accelerated systems. About 2/3 of the list are still simply driven by systems which do not use any of those accelerators. And I even broke out that share of, in red, that share of systems which use the Xeon Phi as their only processor, because we don't count them as accelerated. But even if I mix those in, the fraction of accelerated system doesn't go above 1/3 of the whole list. So we expected more. It's a sign that these technologies still haven't made their breakthrough, haven't had their breakthrough in commercial applications, which is a large part of the lower end of the list. And it's going to be interesting to see if that happens. Maybe with machine learning, if we have more machine learning systems, that's going to happen. But so far, it hasn't. So we have been working with the Green 500. We have combined the data sets, and we collect the data together and publish that together. On the web right now, we have a similar effort with HPCG. On the web right now, if you go actually to the database interface, you can create a list, and you get an option how you want to sort the list. If you want to sort it by HPL, if you want to sort it by power efficiency, or if you want to sort the list by HPCG. So that's fully integrated, and that's something we're going to continue. And all I'm going to do here is show the top systems in terms of how they come out of the database. Right now, there is going to be a much more in-depth treatment of the subject tomorrow in the Green 500 BoF session at the same time. As the Green 500, the top list systems in the Green 500 are driven by technology, we see a very much larger turnover in terms of new things at the top, because new technology comes in, and even if it's a small system, it can immediately be the number 1 in the Green 500. So it shouldn't be surprised that half of that list is yellow, as in new system. It's actually surprising that it's not more than half of the list. We have seen 80 or 90% of that list being totally new system. And what you see at the top is 4 of those 5 new systems on the very top of the Green 500 are Zettascaler 2.2 systems. They all have the same architecture, and they show up on different locations in the list. And then the number 5 in the Green 500, Yoko, is actually the number 4 system in the top 500. So they are featured very well in the top 500 as well. The other 5 systems have been on the list before, including the previous number 1, Tsubame 3.0, which is now at position 6. The only thing I want to really highlight here is there's in the right-hand column, if you look at the power efficiency numbers, there is 3 entries which have a star next to it. So we introduced 2 years back, we introduced a new rule when we combined our efforts that you can give us 2 sets of data for LINPACK and for power. You can run the same LINPACK on the same system with the same number of nodes, but you can run that same LINPACK size once optimized for achieving high performance, and we use that number to rank you in the top 500. And you can give us a second data set where you run the very same problem on the same system, but you optimize the run for using the least power or for optimizing the power efficiency of the run to get the highest ratio of HPL to power efficiency. And while a lot of people in the community think that it's a losing game, that it's always the fastest execution, which is the most power efficient execution, that is not true for LINPACK on some systems. And we have 3 systems in this top 10 list here, which gave us power optimized numbers, which perform lower on the HPL than they are listed in the top 500, but they achieve higher power efficiency. So those are the systems which have a star next to it. That's related to a new rule we have, and we'd like to collect more of these data simply for the benefit of really analyzing them and seeing how much you can gain in terms of power efficiency if you're willing to sacrifice some energy. Okay? Power efficiency grows nicely on all the levels in the Green 500 or top 500. That's the average of the top 10, top 50, and top 500 for measured power efficiency, not for derived numbers, only measured. That has been growing nicely. But the important part here is, of course, the number 1, and somehow my animation here is off. You see the top 500 average, the blue line at the bottom, and the red dots, which is the number 1 on the Green 500. And the number 1 on the Green 500 has really pulled away nicely from the average in the top 500, which is important because we need these architectural innovations and the improvements in power efficiency if we ever want to go to get close to that exascale system with 20 or 30 megawatts power consumption. So the new winner we already counted was the Zettascale 2.2 system. And with that, I already mentioned that we have integrated the HPCG performance collection into the top 500. Coming June, hopefully you're actually going to be able to submit your data there too. So far you have to send them to Mike and or Jack. And to talk a little bit about the HPCG, I'm going to call up Mike now.
Thank you. Thank you, Eric. Hear me okay? No?
So that's Mike Haru. Just say, talk. No, don't touch it. Just talk. So then
All right.
reach Mike.
There you go.
Now? Can you hear me? Yes. Okay, very good. Thank you. Thanks, Eric. We have just a couple of slides on HPCG, saving 90 minutes from the BoF for this, so we're happy to be here and be a part of this event. The results have already been posted. We'll just show you the top 10 systems, and we'll be handing out awards in just a minute here. So probably the most notable thing is the significant remixing of the top systems, showing that HPCG does represent different performance characteristic and signature of these systems, and gives us some interesting mix of information to reason about what performance systems might be like. In particular, this notion that we introduced several years ago of bookends, of thinking of HPL as the high end of what a system could achieve, and HPCG thinking of it as kind of the low end of realistic application performance, seems to be holding out and seems to be a reasonable way of thinking about these two benchmarks as a pair. Some highlights from this are the top 10 machines have a serious rearrangement based on compared to HPL. The US is now part of the top 3 club. The Trinity system in particular has an upgrade, and with HPCG we're able to see that benchmark run on both parts of the system. It has both a strong Haswell and a Knight's Landing portion to it, and the benchmark was run on both parts simultaneously, same MPI communicator, slightly different problem sizes on each half because the size had to be a little larger on the KNL to get peak performance, but it was still a globally consistent three-dimensional domain, and a single system of equations was solved. And so that was a significant result. I anticipate with this benchmark and the systems where you have host processors and accelerators, that there's a significant amount of memory system performance on the host processors, and HPCG can take advantage of that. And take advantage of that on both the accelerator and on the host systems. And so running the benchmark using both types of devices, or even more than two maybe in the future, is a significant future for HPCG and a significant way of looking at system performance. Pete Stein received an upgrade this past year and slightly improved its number, which put it ahead of Taihu Light. Tsubame, you can see, with 4 times improvement. The first results on Skylake cores and first Volta results. And for me, the funnest one is our first result in space. It's kind of fun to think about our software being run off-planet. And I'll stop there, and then we'll just invite our 3 top winning system, the team members from that up here. Number 1, again, is the Riken Fujitsu system, the K computer, and we would ask them to come up at this time and receive their award. You can clap.
You can clap. Congratulations.
Congratulations. Yeah. Congratulations.
Okay.
Yes.
Okay.
Thank you.
Congratulations.
Bye-bye. Thank you. Number 2 is the.
Yeah, why not? Take it.
Yeah, go ahead. Number 2 is the Tianhe 2 system from NUDT. Yutang, please come up. Thank you.
Congratulations. Okay. Very good.
Thank you. And number 3 is the Trinity system from Los Alamos and Sandia. We have a couple of representatives here for that.
Oh, here we go.
Jim Luhan and Scott Hemmer.
Congratulations. Congratulations.
Congratulations, Jim.
That's right.
Congratulations, Scott.
You've done
Yeah,
that.
very good.
I do this, and nobody's taking pictures. Oh, there they are. They're there. Okay. Thank you.
All right. Thank you. Thanks.
That concludes this.
That's it. That's it.
Is that the end?
Prabhat.
Rabat.
So I'm going to switch slides for a second.
I'm going to do that now, I think. I'll be back. But I'll
There you
exchange.
go.
Sounds good, thanks.
And Horst is going to do the introduction to our next speaker.
So as promised and announced earlier this afternoon in the invited speaker session, we wanted to talk about some potential new applications areas, and in particular machine learning. And for that reason, I invited my colleague Prabhat from NERSC to give us a summary of what NERSC has found out in terms of using machine learning techniques, deep learning in particular, for scientific applications, and some ideas and thoughts about how this could lead to a benchmarking activity. So Prabhat, welcome, and
Great.
we're looking forward to your talk.
Thanks very much, Horst. So I guess before I dive into benchmarking and deep learning, I think I wanted to make the general comment that data and simulations are equally important for science going forward. While, of course, historically this community has focused on high-performance computing and simulations, we do believe that statistics, machine learning, and in particular deep learning are going to be critical for scientific discovery. So I'm just going to share some preliminary thoughts on what are the considerations for thinking about benchmarking deep learning. But before we dive in, just in case you've been not following the media recently, I would say that in the last 5 years or so, probably the single most important development in computer science is the rise of AI and deep learning. A number of difficult benchmarks have been beaten now by deep learning-based systems. So the ImageNet competition, which is around finding objects and images, has now been comprehensively defeated by deep learning systems, to the extent that now these systems are more accurate than human-level performance. The same trend is true for speech recognition. A number of researchers in Microsoft and other places have been working on systems for recognizing patterns in speech, and now deep learning-based systems are readily able to beat human-level performance. In the area of control systems, self-driving cars are not science fiction anymore. So at least in California, you see a number of cars from Google and others routinely driving in highways. And finally, I think the big moment of our generation, just as Garry Kasparov was defeated by Deep Blue a while back, for our generation, the system of Go, the AlphaGo system developed by Google, has now comprehensively beaten the human experts. So a simple question that we asked ourselves around 4 years ago was, I mean, all these case studies are great, but we fundamentally care about science at NERSC and other supercomputing centers. So can deep learning work for science? Is it even relevant? So I'm just going to go through, in brief, just touch upon a few case studies that show that deep learning indeed is relevant and can obtain state-of-the-art performance. So if you look at astronomy data, modeling galaxy shapes can be done effectively by deep learning. If you look at cosmology mass maps or the output of cosmological n-body simulations, we've essentially discovered that deep learning systems, in particular a variant called the generative adversarial network, can capture all of the underlying statistics in cosmology simulations, to the extent that you can use a trained GAN to synthetically generate new cosmology output. In the field of neuroscience, we've discovered that you can train a network to learn patterns in ECOG data and automatically synthesize speech. In genomics, new devices like the Oxford Nanopore are now being deployed in practice. And we've discovered that you can take raw, noisy waveform data from the Oxford Nanopore and accurately predict ACCEG, or genome sequences. In climate, both for simulation output, but also for satellite data sets, you can reliably find patterns and automatically track them in space and time. In high-energy physics, if you look at the raw LHC calorimeter data, again, discriminating between background and signal can now be done with deep learning more accurately than what physicists have been doing for a decade or more. For the Diabase neutrino data set, we found that you can do clustering effectively with deep learning, but also discriminate between 5 different kinds of particles. Similar results have been obtained for ELISE photon discrimination problems. And now we're also starting to look at replacing Kalman filters in the LHC with LSTM models. So beyond these 6 or so case studies, and again, we have many more at NERSC, and other national labs have their own case studies in quantum chemistry and so on and so forth. What does this really mean for science broadly? So in this slide, I've sort of captured the various applied offices in the DOE. So problems in astronomy, cosmology, and particle physics in high-energy physics applied office, in climate and genomics, and biological and environmental research, from light sources and material science in basic energy sciences. And then you might have output from particle colliders in nuclear physics or plasma physics in fusion. Now, when we talk to scientists and we ask them, what are the problems you want to solve in all of these different areas, the problems range from pattern classification problems to regression problems. So those are examples of supervised learning problems, but also clustering and dimensionality reduction problems. So those are examples of unsupervised learning. People are interested, so despite all of the great computing power that's now available, people are interested in cheap simulations, because it is prohibitively expensive to densely sample large dimensional parameter spaces and launch jobs that take 10 million core hours for one parameter combination. So people are interested in surrogate models or designing experiments so that you can more intelligently sample this space. Finally, feature learning is extremely important, so that's a prerequisite for any supervised learning problem. And then anomaly detection is critical. Typically in particle physics, you can essentially win Nobel Prizes for detecting interesting anomalies. So if you look at this broad landscape of various science areas and the kinds of challenges that people have, the stuff shaded in blue is essentially what we think now deep learning can solve fairly effectively if you have enough training data. So I think what we found is that for pattern classification and regression problems with enough data, deep learning can be quite effective. I don't think we're ready to declare success on clustering and dimensionality reduction yet. There's more work to do there, in particular having to do with interpretability. But certainly, I think reinforcement learning algorithms can be applied to designing experiments more intelligently. And finally, I think one conclusion that we've certainly derived over the last 4 years is that maybe as humans, we probably rely too much on our capability to design features. And this is something that deep learning has, I think, conclusively proved in the field of computer vision, that deep learning can do a much better job at that as humans. So I would say that that row is definitely captured. All right, so given that this is already happening, again, I think we are just at the beginning of the application of deep learning to scientific problems. Should we think about creating a deep learning benchmark? So why would we do that? One, when we at NERSC, and again, other supercomputing centers around the world, when we have a procurement process, we do need to accurately capture and characterize our workload. And I do believe that going forward, machine learning and deep learning is going to be a critical part of our workload. There is a training component. Again, a lot of the emphasis so far, at least, has been on training. But we do believe that trained networks are going to be deployed in practice. And then you're going to essentially stream data to wherever that network might be and solve your regression or classification problem. So both of these aspects, I believe, are going to be important. I think it is really important that we, the science community, capture realistic science use cases as opposed to commercial applications. Again, the industry has been doing this for 5 years now. There are well-established benchmarks like AlexNet and ResNet 50 and others which are in place. But we need to stay true to our science use cases. We have complicated data that's 2D, 3D, 4D. Sometimes the data is sparse, sometimes it's dense. Sometimes you have the object that you're operating on is a graph. So anyway, so we have to make sure that that complexity is captured in the benchmark. And then finally, a lot of what is done in the industry tends to be around single node. So you're doing your training or maybe your inference on single node. But we have much larger data sets. We will almost certainly have to use many nodes, tens, hundreds, maybe thousands of nodes, and run deep learning at that scale. So clearly, the software is important. Again, when we think about a benchmark, staying true to what deep learning frameworks are being used by scientists in practice is important. I'll note that these frameworks have not been developed by the HPC community. These frameworks have been developed by the data science community, which may not have a very strong background in HPC techniques. So there's a lot of room for optimization there. And then there are certainly hardware implications of such a benchmark. Is a CPU the right architecture? Is a GPU the right architecture, or an FPGA or something else? So that's an important question. So from a facilities perspective, we believe that all of these questions are important. All of these considerations are important. So as you think about a deep learning benchmark, and I think Horst had motivated this in his slide, one can ask questions of the kind, is deep learning isn't it just GEM? And if so, isn't it sufficient to just run HPL? In particular, if one were to come up with a comprehensive deep learning benchmark suite, would that really change the top 500 rank order? So it's clearly early days, I think, to reach a definitive conclusion on all of these three questions. But I'll just say, I think that it is probably warranted at this point in time to conduct an in-depth exploration of what deep learning for science looks like, and then then try to see if these three questions can be addressed. All right, so I'm just next few slides are going to delve into some similarities and differences between a potential deep learning benchmark and HPL. So in terms of similarities, it is true that the majority of the time is likely going to be spent in a GEM in a deep learning benchmark. Almost by definition, that kernel is going to be highly optimized by the vendor, and there is likely going to be a high degree of correlation between a deep learning benchmark and HPL. So that is true. But I'd like to focus on a few differences in the way deep learning is done right now and HPL. At a high level, deep learning benchmarks are not going to be around the flop number. Convergence of these architectures have to be taken into account. So for example, you can almost naively boot up an architecture, go the data parallel route, and have no synchronization whatsoever across nodes. You're going to get perfect scaling, but your networks are not going to converge at all. And fundamentally, the thing that you care about as a deep learning practitioner is the predictive accuracy of your network. So any benchmark will have to take into account this convergence aspect. The bit precision issue is interesting in deep learning in that I think a lot of intriguing results from the community that you can get really good predictive accuracy even by dropping your precision down to 16-bit or 8-bit or even lower. So again, if predictive accuracy is what you care about for the network, then maybe sticking to 64-bit or 32-bit is not important. So that's an independent degree of freedom that I think deep learning practitioners want to explore. And almost certainly, I think vendors are going to explore this. Your data sets might be dense or sparse, but also your network might be dense or sparse. So the compute and communication patterns might be complicated. Right now, data parallelism is what is employed routinely. But going forward, chances are high that your model is not going to fit on a single node. So when you think about model parallelism, which is breaking a network up into pieces and spreading that out across nodes, the communication patterns there are going to get interesting. Finally, when you think about weak scaling deep learning, there are some additional considerations having to do with better hyperparameter tuning for getting your network to converge. So I want to dive into a little bit of detail on the compute side of things as to how the compute is different between deep learning and HPL. So as you think about a single node, so again, let's say that you're going with a data parallel approach, your entire network fits on a node. And then as you proceed with these convolution and pooling layers, the form factor for these matrices actually changes as you go across layers. So in this diagram here, essentially we've listed out that you start off with an extremely tall and skinny matrix to begin with, but the form factor for that matrix sort of improves as you proceed in time. This is in contrast to HPL. Obviously, it is harder to optimize for tall and skinny matrices. And I'll also note that some of the layers can be compute bound, but others can be memory bandwidth bound. So overall, this is a more complex workflow to optimize. Some of the layers, particularly having to do with pooling or applying the nonlinearity ReLU or batch norm, there's really not a lot of compute there. So they are definitely bandwidth bound. And all of these, the logic pertaining to these layers is quite critical in your deep learning benchmark overall. On the communication side of things, at least on the deep learning front, essentially you need an all-reduce. That's extremely effective. The size for your all-reduce might change, so it might be in the order of megabytes or hundreds of megabytes. But fundamentally, when you go to a model parallel approach, when you're breaking the network up, the communication patterns there are going to get really interesting. So it's going to be an all-to-all. So there's more complexity there, I think, going forward. All right, so I'm just going to end with this quick slide, which is that there is a lot of innovation going on right now in the deep learning space. New frameworks are available every other week. People have essentially given up on conferences as them being too slow in terms of capturing the latest and greatest, and people just put up papers on archive and send out a Twitter feed saying that you published this. So almost certainly there will be new applications in science or in the industry. There will be new frameworks. There will be new architectures. By no means is the space of architectures set from here on going forward. So there is a challenge, I think, in terms of designing a deep learning benchmark, in that do you want to capture the high-level framework, or do you want to extract out the low-level motifs and somehow compose them? So anyway, so that's an open question. And as I mentioned, in terms of the architectures, there's going to be a lot of diversity going forward. The reproducibility issue is interesting across scale. So stochastic gradient descent is stochastic by nature. And certainly, as you change the scale of the problem, the convergence behavior changes. So one will have to think about how do we make sure that the network, under varying degrees of parallelism and data set sizes, gives you the same answer. Now, related to data, again, you would prefer to operate in a regime where you control the data, you know the real problem that you're after, and you know what the target accuracy might be, say 95% or so. But that is harder to parameterize. So if you create synthetic data, however, the convergence issue is maybe not as interesting. So you'll have to think about, if you want to go down the synthetic route because it's easier to parameterize and create larger data sets, how do you take into account convergence and how do you take into account reproducibility? Finally, a lot of the effort right now is around training. But going forward, we do believe that there are interesting use cases for inference. Deploying the trained network, maybe at a lower level of precision, next to an instrument, or maybe on a supercomputer, that's going to be something to consider. So I'm going to stop at that. So again, I think Horst had asked me to just lay out some thoughts. It was not going to be a concrete proposal on, use this architecture for this particular problem and aim for that as a benchmark. But I think the purpose of this presentation is to just enumerate some issues. I know that there are other benchmarks in the field. So we have the deep benchmark from Baidu and The Argonne folks and other teams have worked on the candle benchmark. But I believe that an in-depth investigation of this issue is warranted going forward. Thank you.
Thank you, Parad. So we've reached the question and answer session part, and maybe just in previous sessions, if you would like to pose a question both on the machine learning part or top 500 or green 500 or HPCG, please step up to the microphones, then introduce yourself and pose your question. We have microphones 1, 2, 3, 4.
Jack,
Okay. Everybody wants to go? Everything clear?
6:15.
That's surprising. This group always had lots of questions. So, going?
So after 25 years, the community has run out
You're
of questions.
tired, right? Okay, going. Gone. Have a wonderful evening, and please, if you do have questions you don't want to ask in front of a big audience, come up front and ask us in a small, more convivial group. Thank you.